Okay, today let's look at the PFET. So last time we looked at the NFET, we looked at the regions of operation. So now we're going to look at what we call the complementary device, the PFET. And structurally this looks very similar to what we saw before with some important changes here. First of all, the drain and the source, the diffused areas are P-type, not N-type. And the bulk underneath the channel is N-type, and we call that an N-well. The reason being is that we are still putting this structure inside of a P substrate. Now, some people might ask, why don't we just have an N substrate? Because we want to be able to manufacture both NMOS and PMOS devices together. So, if I wanted to add an NFET, I do it just like this. So now I've got my P substrate, I've got my N plus drain and source diffusions, and now I can put them both in the same substrate. So that's the purpose of that well. It enables us to manufacture both PFET and NFETs together on the same substrate. And as we're going to see later on, that is extremely common and important in modern circuit design. In fact, adding PFETs and NFETs together gives us something called CMOS, which stands for complementary MOS. In other words, NMOS and PMOS together. So, this is what we do modern design with, and in fact, when we start looking at circuits designed with MOS transistors, we're going to be looking at complementary type designs. Because it turns out having both PMOS and NMOS available makes things much easier for a lot of circuits. Okay? So, let's now focus on the qualities or the properties of the PFET itself. So for PFET, much of the mechanism that we looked at before for the NFET is the same. We're going to form a channel underneath. Except in this case, we're going to form a P channel. We're going to attract holes underneath the gate instead of attracting electrons. So the basic concepts are the same, the mechanisms are very much the same, but we're flipping the carriers around. Holes instead of electrons become the carriers in the channel, and we're also flipping around the polarities of the voltages to make this happen. So for the PFET, we have the following. We need the gate source voltage to be negative. And in addition, the threshold voltage is negative. The drain source voltage is going to be negative. VGS must therefore be less than VT. It has to be more negative than VT to turn the channel on. And VDS has to be less than or equal to VGS minus VT for saturation. Now this may seem a little bit confusing right now, but once you start working problems, this all sorts itself out very quickly. Once again, I want to emphasize you're going to have all of these equations in front of you. You're going to have the diagrams, okay? It's all on, if you've looked, hopefully you've all looked at the equation sheets on Brightspace you're going to have available for you in the exam. So you can see you have all this given to you. So again, it doesn't come down to memorization, but you do need to understand how to use this. And the best way to learn how to figure this stuff out on your own is do the homework. Okay? So the book Our textbook does not like negative numbers, or the authors did not like negative numbers. Some textbooks are fine with using negative numbers for PFETs, negative voltages and such. But our textbook writers didn't like it, so they like to rewrite things in terms of positive values, which means they use a lot of absolute magnitudes or they flip around the subscripts. So to avoid negative voltages, you'll see that our textbook flips around the subscripts. Instead of saying VGS, VG minus VS, for PFETs they use VSG, VS minus VG, because that's a positive voltage. And then they'll say that it has to be greater than or equal to the absolute magnitude of the threshold voltage in order to turn the PFET on. And along the same lines, instead of using VDS, our textbook likes to use VSD. And in this case, saying VSD is greater than or equal to VSG minus the absolute magnitude of VT, that is our saturation boundary condition. Now, you don't need to do it this way. You can actually use negative numbers, and you can actually use the same equations for PFETs and NFETs almost entirely, and you'll get exactly the same answer. But again, the authors of our text didn't like that, and so you'll see they like to have all positive numbers, and they flip these around. So although the textbooks I've used, we use the same equations, and we didn't worry about the negative numbers, since Sutter and Smith chooses to do it this way, that's what we're going to follow in the lectures, because I don't want to deviate from what's in the textbook. But you'll see other textbooks that use exactly the same equations. When you take negative numbers and multiply by negative numbers, you still get positive values, and that's exactly what happens. Now, note also, because of the fact that we're using these negative numbers and the fact that VSD is a positive number, the flow of drain current is from the source to the drain. Flow of positive drain current instead of from drain to source. All right? All right? Now, a couple other differences. Our transconductance parameter we had for the NFET, we're going to have a different transconductance parameter for the PFET. Instead of K sub n prime, we're going to have K sub p prime. And this, of course, indicates the fact that holes are now the majority carriers in that channel when we do the inversion of the channel. All right? But what's interesting about this is, remember, K sub n prime was equal to mu sub n times Cox, which is the mobility of electrons. Over here, K sub p will be equal to mu sub p times Cox, the mobility of holes. Turns out that electron and hole mobility are not equivalent. Which do you think is more mobile, electrons or holes? Electrons, yeah, because electrons are actual particles. Holes are simply, they're pseudoparticles. We pretend they're a positive particle, but really what they are is they're a hole in a covalent bond, right? There's a missing electron in a covalent bond. So a hole does not move as readily as a free electron just traveling through the lattice. And so therefore what we find is mu sub n is typically anywhere from 2 times mu sub p to 4 times mu sub p. Electron mobility is much higher than hole mobility. And so consequently, the transconductance parameter of an NFET is going to be larger than the transconductance parameter of a PFET. Now, you may ask, some people may ask, gee, doesn't that mean we'd rather use an NFET than a PFET? Well, sometimes it does mean that, but it still turns out that having those PMOS devices is extremely useful depending upon the circuit you're going to have. All right? But what this tells us is NFETs will generate larger values of drain current than PFETs, all else being equal in terms of geometry and voltages, and geometry and the magnitudes of the voltages. So all else being equal, assuming the same voltage magnitudes, not polarities, but the same voltage magnitudes, and assuming the same device geometries, the same widths, lengths, we'll find that NFETs have higher drain currents than PFETs do, all because of the different transconductance parameters. We're also going to see, turns out that NFETs have higher gains and faster speeds than PFETs. But again, that doesn't mean PFETs are useless. It does mean that in some applications we prefer a PFET, or rather an NFET over a PFET. But as we're going to see later on, complementary design makes it very important that we have both types of devices available to us. All right? I'm going to ignore that. Okay, so any questions? Yeah. Oh, when we start building amplifiers, I mean, you'll get more amplification. You can get more amplification out of a basic transistor using out of a basic amplifier using an NFET rather than a PFET. We're going to see that later on. And it all, once again, comes down to the transconductance parameter being higher. Yes? Okay, all right. Yeah, we'll get to this later. Okay, we will understand later on what I mean by this statement. All right. All right. Other questions? All right, well, let's quickly write down our equations. I'll just leave that here for the moment. So what are our current equations for PFETs? In the triode region, ID is equal to K prime P times W over L times VSG minus the magnitude of V sub T times VSD minus 1/2 VSD squared. And note once again how I'm flipping the subscripts around to change the polarity of the voltages, and I'm putting the magnitude around that threshold voltage. For saturation, we get this, 1/2 K prime P W over L times VSG minus VT magnitude squared. And once again, note that the transition from here to here is that VSD is equal to VSG minus the magnitude of VT. So we have the same boundary condition that goes from triode to saturation. All right? Now, like I said before, the book likes to do this because it wants all positive numbers. The authors had this thing about wanting positive numbers. But if you think about it, what if I had to write the equation this way? What if I were to use the same form for the equation that I used for the NFET? VSG minus VT. Well, let's think about this. Let's assume that VSG was 2 volts and the magnitude of VT was 1 volt. 2 minus 1 is equal, squared is equal to 1. But let's assume we used this. I'd see minus 2 minus negative 1. I get negative 1 squared as opposed to 1 squared. What's the difference between those two equations as far as the answer I get? None. That's what I'm saying. Some books don't bother to do this. Our textbook does, but you'll find other textbooks, they'll use the same equation form. They'll just flip around the Kn for the Kp. And they'll just say, hey, you're going to square this anyway. So whether it's a negative number, once you square it, and you're going to be squaring it regardless of whether it's triode or saturation, you're going to get a positive drain current. So some textbooks don't bother. Our textbook makes a distinction. But again, because our textbook does use these equation forms, I'm going to use those as well, just to avoid confusion. But other textbooks will not. All right, what are our boundary conditions for this? Well, let's go ahead and let's write our boundary conditions. I actually want to compare both the NFET and the PFET boundary conditions. So for NFET, for an NFET to be on, VGS has to be greater than VT. For a PFET to be on, VSG has got to be greater than the magnitude of VT. Or, here's another way to think about it. I could also say the magnitude of VGS has to be greater than the magnitude of the threshold voltage. Sometimes that's a better way to think about it with PFETs. You know, your people get mixed up with the negatives in PFETs, but sometimes it's just like, okay, is the magnitude of the gate source voltage greater than the magnitude of the threshold voltage? They're both negative, but look at the magnitudes. If that's the case, then your PFET's going to be on. So it's a kind of a different way to think about the problem, or to think about that boundary condition. An NFET that is saturated VDS will be greater than or equal to VGS minus VT, as we've already talked about. For the PFET, VSD will be greater than or equal to VSG minus the magnitude of VT, which we've talked about before, okay? Or you can think of it this way. The magnitude of VDS has to be greater than the magnitude of VGS minus VT. So again, think about it in terms of magnitude. Is the magnitude of the drain source voltage larger than the magnitude of VGS minus VT? Just a different way of thinking about it. All right? So people tend to struggle a little bit more with PFET equations versus NFET just because the signs get them mixed up. But once again, the equations will be in front of you on the exam. You don't have to worry about memorizing anything. Working the homework problems and learning to be comfortable with those equations is going to be the best thing you can do as we start preparing for the exams. All right? Questions? All right. Let's now consider if we're going to put a MOSFET in a circuit. Oh, yes? I'm going to give you actually in both forms. I'll give it to you, and from a second textbook, I'll actually include the exam equations. If you look in the equation sheets, you'll see some equations that don't come from our textbook. Come from another textbook. In that textbook, the authors just use the same equations. So if you want to use those, you're welcome to. So I include them both, whatever you feel more comfortable with. You will get the same answer. You're going to square the number, so whether it's positive or negative, you get the same answer when you calculate ID. Any other questions? All right. Well, let's consider if we're going to put, yes?
So I was wondering one thing. So VSG is like the voltage of S minus the voltage of G, right?
Yes, V sub S minus V sub G.
But are those like completely independent, or they sometimes depend on one another?
Well, VSG is going to be set by the voltages you apply to the MOSFET.
Yeah, but is it possible to have like one voltage, like one voltage depends on like what's going on to the other one, or are they completely independent?
Well, it depends upon the circuit and how you connect the circuit. I mean, is it possible for them to be related? Well, you want VGS or VSG typically to be a constant voltage because you're trying to set a bias, right? So it depends upon the circuit you're trying to build. But yes, it's certainly possible to do it that way, but it's a function of what you connect it to. As we start learning how to bias and analyze MOSFETs, this will become a lot clearer to you. So let's look at circuit symbols. And when I talk about circuit symbols, I want to point something out that a lot of people get tripped up by when they do LT spice using PFETs. All right. What does a PFET or an NFET look like? Well, actually, it depends upon the manufacturer, the data sheet, and the textbook, how they draw MOSFETs. There are actually different ways MOSFETs are drawn. Unlike things like resistors and voltage sources and capacitors and inductors, there's no uniform symbol that everybody uses. So you'll see that one of the symbols that's used very often is the symbol of the three-terminal device. Actually, well, first let me cover the four-terminal device. Let me do that first. Since that's what we've already looked at. So for an NFET, I'm drawing this as a four-terminal device: drain, source, gate, and the bulk. All right? for the PFET, source, drain, gate, bulk. Now notice, I'm flipping the source and the drain. And this all comes down to the convention that we use whenever we are drawing schematics. Now, you guys have probably gotten used to this. But you know, when we draw circuits, we normally start at the most positive voltage at the top towards either a negative voltage or a ground at the bottom of the schematic. And the reason for that is this lets us define positive currents flowing from the top to the bottom of the schematic. It's convention. Everybody does it that way. Because PFETs have positive drain current going from source to drain, the source is going to be connected to a more positive voltage than the drain. And so we draw this PFET, in effect, upside down compared to the NFET. Now, I point this out because when LT-SPICE, when you get a generic LT-SPICE model and you drop it into a schematic, you'll find that LT-SPICE always assumes that the source is on the bottom. And it will flip the transistor upside down. So watch out for that, because you've got to, before you connect it into your circuit, you've got to literally flip that symbol. So LT-SPICE always assumes drains on the top, sources on the bottom. And you'll see when we get to bipolar transistors, same thing. Collectors on the top, emitters on the bottom, which messes you up with the P-type devices. So you always have to flip that around. I've seen more than one student over the years come to me and say, Dr. Holman, this circuit isn't working with a PFET. PFET's upside down. They just pulled it out of the schematic, dropped it in, and didn't think about where the drain and the source were. So this is our 4-terminal. It's our 4-terminal symbol. And of course, with this, we can go through and we can define voltages and currents. Positive drain current in both cases flows into the top and out the bottom. So the thing about FETs is what goes into one end of the channel comes out the other. So the same drain current goes through. No current goes through the gate. The gate has an insulator. So the only purpose of the gate is to apply a voltage to create the channel. There's no gate current. All right? In addition, I can define VGS, gate source voltage, VDS, drain source voltage, and in addition, I can define VSB, the source to bulk voltage, if there is a potential difference between those. And there can be if you have this 4-terminal device. What you're saying is you're preserving the ability to connect the bulk and the source to different voltages. For the PFET, in this case, VGS will be gate to source, VDS, drain to source. But again, if you define it this way, our book doesn't like it. Our textbook prefers to do this, to flip the polarity around and define VSD, because the source is more positive than the drain. The source is more positive than the gate. So VSG. So as I said, the book does this, but once again, you can do it either way. You can define it either way. You'll still get the right answer, the same answer if you do it correctly. And just as we saw before, I can have VSB. Or again, I can flip it around and call it VBS. So I can always flip the polarity and flip the order of the subscripts, and do that for PFETs as well as NFETs. So watch out, especially with PFETs. Make sure what you're looking at in terms of the order of the subscripts. All right. So this is one way of drawing PFETs and NFETs. But there's another way. In this case, this is the three-terminal symbol. And the three-terminal symbol assumes that the source and the bulk are connected together. So VSB is equal to 0. So source connected to bulk, therefore I draw it this way. So there is assumed, but typically not shown in the schematic, the source and the bulk are the same, although usually it doesn't bother to draw B. If it's drawn this way, you can assume the source and the bulk are the same terminal. And for the PFET, you draw it this way. Now, I want to point something out. Notice the directions of the arrows. Why are the arrows drawn the way I've drawn them? Well, the direction of the arrow indicates whether you're talking about something that's going on in a p-type or an n-type semiconductor. If it is pointing out, then you're typically talking about an n-type. If it's pointing into the device, you're talking about p-type. All right? So here, the arrow points in. What is the bulk in an NFET? Is that P or N-type? P, yeah. It's a P-type bulk, a P-type substrate. So this arrow pointing in says the bulk is P-type. It's an NFET. The drain and the source, therefore, must be N-type. Over here, it's an N-well. The bulk is an N-well. The arrow points out. But I go over here, the arrows flip, which sometimes confuses students, except over here, now the arrow belongs to the source. What is a source in an NFET? It's N-type. What is the source in a PFET? It's P-type. So it points out and in because now it's connected to the diffusions, not to the bulk. So sometimes people get a little confused about this, but once again, pointing out it's N-type, pointing in it's P-type. Yeah?
Is PFET the same on LG specs where you have to rotate it?
I think if you actually pull out a three-terminal device, it's going to be the source on the bottom. I'm almost positive. And they may have changed that in the more recent versions, but the last time I tried and looked, then the PFET was on the top, or rather the source was on the top. You've got to be careful about that. So look, because if you do pull out a three-terminal device, you may find the source is on the bottom, and look for the arrow. The arrow is going to be associated with the source. But again, I've seen people do that many times, and it causes all kinds of problems. Okay? So, you see these. Now, they're actually, I wish I could say this is the only way people draw NFETs and PFETs. Well, they don't. Sometimes you'll see the NFET drawn just like this. And why do they draw it that way without any arrows? They say, well, it's an NFET because the PFET looks like this. Put that little bubble in front of it. So that's the PFET, that's the NFET, and the reason why we don't bother to do the drain or the source is because if they're symmetrical devices, the drain will be the more positive of the two diffusions, so the one on top's got to be the drain. If it's a PFET, the source is more positive, the one on the top's got to be the source. This type of schematic drawing technique, you'll see this used a lot more in digital design. So you'll see some manufacturers do this. Incidentally, what does that bubble remind you of? Anybody who's had digital systems? Yeah, it's an inversion, right? So what they're saying is the same voltage applied to a gate turns on an NFET, turns off a PFET. So that's the not symbol. So you'll see this too. And I wish I could say this was the only. There are others besides this. Other manufacturers, other textbook writers will have different symbols for NFETs and PFETs. But these are the most typical that you're going to see, the most common examples. But don't be surprised if you look in a technical paper and look at transistors that are drawn in some way you've never seen. They're using some convention of their own. So with MOSFETs, things are not quite as established as far as conventions as with other components. All right? Questions? All right, let's talk a little bit about one more phenomenon before we start drawing circuits. I want to talk about one quantity or one parameter that's going to change our equations. And that's the phenomenon of channel length modulation. And we talked about this last time. Ideally, for an NFET, we should get the following. K prime N over 2 times W over L times VGS minus VT squared. This is the ideal equation because it is independent of VDS. So as we mentioned before, that's a square law equation, but remember I said before, it's not really true. It doesn't stay perfectly flat. We actually see a slight increase in ID as we increase VD. In an actual NFET, we see a slight increase. So as VDS increases, then ID goes up slightly. We therefore need another equation, a better equation to describe that. So I'm going to write a new equation, and I'm going to add another factor to it. ID sat is equal to K prime N over 2 times W over L times VGS minus VT squared times 1 plus lambda VDS. And that's a little additional term on the end that now incorporates that VDS term. Lambda is our channel length modulation parameter. And notice, lambda times volts, I want the units to cancel. So this needs to have an inverse volts unit. Now what does this show? This simply illustrates that as our drain becomes more positive, the geometry of the channel is affected. Even though we're pinched off, ideally once we pinch off, the channel geometry shouldn't change, but actually there's a second order effect that does cause it to change slightly. And so therefore we get this current term. Now for PFET, well, actually I should say, first of all, for an NFET, lambda should be greater than 0 for an NFET. For a PFET, lambda is going to be less than 0. So in this case, once again, because the book likes to use positive numbers, we're going to use the absolute magnitude. And so in this case, what we're going to get is ID sat is equal to 1/2 K prime P times W over L times VSG minus VT squared absolute magnitude times 1 plus absolute magnitude of lambda times VSD. So there's our PFET drain current equation, in this case using our flipped subscripts and our absolute magnitudes. So NFET, PFET. Now, let's think about conductance. Remember last time we derived conductance and resistance in triode region? Let's consider how conductance works in saturation. Let's look at the NFET. Let's consider the conductance between drain and source in saturation for the ideal case. So GDS is the derivative of ID with respect to VDS. If I've got the ideal equation, what is the conductance? What's the change in ID with respect to VDS? 0, isn't it? There's no VDS term. If I take the derivative, it's just a constant. I just get 0. So for the ideal case, then GDS is equal to 0, and therefore RDS ideal is equal to infinity. So in saturation, the drain source resistance is infinite in the ideal case. Obviously, that's not the case for a true NFET or PFET, because now we have to actually incorporate that channel length modulation term. And so in this case, I'm going to write some new equations. So if we consider output conductances or resistances due to lambda, then GDS or G sub O, instead of GDS, we'll typically call this G sub O, the output conductance. It'll be the derivative of ID with respect to VDS, and that'll be equal to lambda times ID for the NFET. If we take our equations and do that derivative, I'm not going to bother to do it, but I'll just give you the result. Therefore, RDS, or R sub O, is going to be equal to 1 over lambda times ID for the NFET. Turns out that number is going to be very important when we start doing small signal analysis with transistors. We're going to use that equation, that resistance value. And along the same lines for the PFET, GDS times G, or G sub O, will be equal to magnitude of lambda times ID. Note that in both cases, ID is a positive value. Drain current's always positive, NFET or PFET. And therefore, RDS, which is equal to R sub O, is equal to 1 over the absolute magnitude of lambda times ID. So we'll be using this later on. Once we get to the small signal model, these become critical to us, these parameters we just derived. Now, I mentioned before, saturation is actually a desirable operating region for MOSFETs. In fact, amplifiers are almost exclusively designed using MOSFETs operating in saturation. We do not use triode or ohmic region operation. That is important when we talk about digitals, and we'll get to digital circuits later on. But for high-gain amplifiers, when we're doing analog design, we're doing high-gain amplifiers, saturation is where we want to be. And so as I said before, these are going to become important. They're going to become critical when we start getting to that point. All right? Now, once again, these equations are all going to be given to you. They'll be on that equation sheet. So don't get caught up in the idea of memorization. I do advise you to start using those equation sheets and start, when you do your homework, pull them out and start using them. Learn where all of the equations are on those equation sheets. All right? It'll be faster for you and you'll be more comfortable on the exam as opposed to pulling out those equation sheets for the very first time whenever you walk in to take the exam. So just some advice, okay? That's why I give it to you early so you can learn where those equations came from and what part of the books and where you can go to look for what you need. All right? Questions? All right, one final thing I wanted to say to you guys. And we talked about putting NFETs and PFETs together on the same substrate to create CMOS processes. I want to make something very clear to you guys. This is a very simplistic image of a cross-section of a modern circuit, modern integrated circuit. Nowadays, we have far more complex structures than this. In some of the newest transistors we have nowadays, we're building what are called FinFETs, where we're literally building the transistor with the channel and the gate above the surface. So we're actually building them as three-dimensional structures. And you will see dual and triple well processes. So actual cross-sections are far more sophisticated than this very simplistic image I drew for you. I'm doing this once again just because it gives you the picture. But when you start looking at modern processes, you'll find things are much more sophisticated than just this alone. So again, Watch what you're doing. You may see technical papers. You may work in more advanced processes one day. You're going to see that this was a very basic and simplistic picture, but the structure of real transistors is much more complex. I also want to point out that we're assuming the drain and the source are essentially interchangeable. In modern circuit design, that's not really true. Quite often you'll see that the drain will be doped and structured differently, have a different geometry than the source. And the reason for that is to allow the drain to withstand larger voltages. So you can build a high voltage device. And so you may see things like it's called the lightly doped drain and different geometries. And the point of that is the drain and the source may not be interchangeable in a modern process. In fact, probably they will not be interchangeable, all right, depending upon the process you're using. So just be forewarned. We are using kind of a simplistic image that was a lot more valid 20 or 30 years ago than it is today. But the basic principles are roughly the same. What we're trying to do here is to learn how to use the equations. All right, so just want to kind of throw that in because otherwise you take a class in semiconductor physics or device physics and you see Professor Shrimp draw something on a board and you'll have no idea compared to what you saw in this class what is being drawn, because Professor Shrimp is going to draw a structure of a much more modern process when he does the stuff in his class. I'm just doing things in a very basic manner. Okay, so let us consider how we are going to analyze circuits. So first we're going to do DC analysis. Before we start doing small signal analysis, first we have to learn how to analyze for DC values and how to determine what the bias point is for a transistor, just as we did with diodes. So let's do that. So what I'm going to do is I'm first going to draw something, and you can see these diagrams in the book. I'm going to draw something that's called a family of curves. And a family of curves is a graphical way of illustrating the different possible bias points, DC bias points for a transistor. So I've got ID and VDS, and in this case, this is an NFET. I'm going to do this for the NFET. So this is a family of curves for an NFET. And what I'm going to do here is I'm going to draw a lot of different curves for ID versus VDS as a function of the gate source voltage. First, I'm going to draw this curve where the drain current's equal to 0 no matter what VDS is equal to. In other words, in this case, VGS is less than or equal to VT, right? We haven't formed a channel, all right? We want to be greater than the threshold voltage to allow current to flow according to the equations, because VGS minus VT has to be positive. So now I'm going to go through and draw some more curves. So what I'm doing in here is I'm simply showing what VDS versus VDS versus ID would be for different values of VGS. So I'll say here this is VGS1, which is greater than VT. This is VGS2, which is greater than VGS1. This is VGS3, which is greater than VGS2, and so forth. So at larger values of VGS, I can fill in these curves. And so if you look at it, I can actually put in an infinite number of lines if I wanted to here, right? Any value of VGS, I can make one incrementally larger than the other, and I can fill this whole thing in. But I'm just going to go through and I'm going to pick different values, maybe 1/10 of a volt or 1/2 a volt or something like that. And I'm going to then draw these. So there's going to be let me do this. There's going to be a boundary condition so as VGS increases, the boundary condition is going to change too. So here's my boundary condition of VDS is equal to VGS minus V sub t. On this side of the boundary condition, I'm in saturation. On this side, I'm in triode. So over here, VDS is less than VGS minus V sub t. Over here, VDS is greater than VGS minus V sub t. So over here, we note that once we're in saturation, this drain current line remains flat even as we increase VDS. Except it isn't really flat. Channel length modulation. Really, the family of curves is going to look more like this. So we're going to see an increase due to the effect of lambda. So this is the actual. The red is really going to be the actual curve. We're going to see that slight increase in ID. All right, so down here, incidentally, just want to emphasize this too. Down here, we're in cutoff. If VGS is less than or equal to VT, no drain current's going to flow no matter what the drain source voltage is. So we're in cutoff down there. So here are three regions: cutoff, triode, saturation, according to the voltages. So this is kind of a map of all possible DC bias conditions or DC operating conditions for a MOSFET. And we are either going to have to figure out where a MOSFET is on that map, so to speak, or we're going to want to design the MOSFET to put it on someplace on that map. That's what circuit designers do. They choose a bias point. And you're going to learn that before this semester's over as well. All right. However, for now, baby steps. Before we can start designing circuits, we have to first learn how to analyze those circuits. And so that's our first job here. So let's consider how we're going to analyze what our analysis method is going to be. And I hope that this will be kind of obvious to everybody based on what you've been doing so far. If I give you a circuit with a MOSFET, can you tell just by looking at the circuit what the operating condition is for that transistor? Well, when you get more experience, sometimes yes, but most often no. I mean, you can draw circuits, I can't figure it out. So if I'm going to use the correct equations for the drain current, I have to know the operating condition. So if the operating region is not known, what do? Make an assumption. So we're going to make some assumption. And what are we going to do then? We're going to solve the circuit based on those assumptions. Then what am I going to do? I'm going to check my boundary conditions. I'm going to check my assumption by looking at the boundary conditions. And if those boundary conditions are violated, obviously I made the wrong assumption. Pick another assumption and check that one. So if I violate my boundary conditions, obviously my assumption is invalid. Pick another assumption, go back to 2. We've seen this before. We did this with diodes. Well, now we're going to do it with MOSFETs. All right, let's try it. Okay, I've got a 3-volt DC source. That is my gate source voltage, VGS. I've got a drain resistor connected between the drain and the 5-volt supply, R sub D. That's 5 kilo ohms. My current is going to flow into the drain of my MOSFET and my NFET, and that same drain current is going to flow through the resistor, right? All right? So, I want to calculate the values of VDS and ID. Now we've got to make some assumptions. I need some parameters for the MOSFET. So let's assume this is given. So it's given that the threshold voltage is 1 volt. The transconductance parameter is 20 microamps per volt squared. The width is 20 microns or 20 micrometers, and the length is 2 microns or 2 micrometers. That incidentally is a shorthand you'll hear all the time. When people say microns in IC design, they're talking about micrometers. For the sake of simplicity, I'm also going to assume that the channel length modulation parameter is small enough to ignore. Just to make my math easier. So I'm going to assume lambda is approximately 0. Normally lambda is not a big number, so I'm going to assume it's small enough. I'll just say it's close enough to 0. Okay. Well, first of all, I need to find the condition. I need to make an assumption about the condition. Okay. Now notice this is 3-terminal, so the bulk must be connected to the source. That's just given because of the way I've used a 3-terminal model. First question, can I at least determine whether or not this MOSFET is in cutoff? Yes. How can you tell? I'm sorry? Say it again. Yeah, exactly. So by inspection, I know it's not in cutoff. Precisely. Why is that? VGS is 3 volts. So 3 volts is greater than 1 volt. I know the NFET is not in cutoff. Which makes sense. A circuit where the transistor is off is not a particularly exciting circuit, right? It's not going to do much, all right? We want to apply power and we want to turn the transistor on. But the question is it in saturation or triode? All right? I have no idea. Let's make an assumption. I'm going to assume it's in saturation. If it's in saturation, then ID will be equal to K prime N over 2 times W over L times VGS minus VT squared is equal to 10 microamps per volt squared times 20 over 2 times 3 minus 1 squared. And I calculate, and that is equal to 400 microamps. Okay. Therefore, what's VDS? Well, VDS must be equal to 5 volts minus the voltage drop across that resistor. So I plug this in for ID, and what I'm going to get is this is equal to 3 volts. And there's my answer. So I've calculated ID and VDS. But do those answers make sense? What do I need to check? I need to check the boundary condition. Is this transistor actually in triode? All right. VDS is 3 volts. VGS minus VT. 3 minus 1 is equal to 2 volts. So is VDS greater than VGS minus VT? Yes. So it's saturated. I check the boundary condition. And everything seems to work. So I guessed correctly. All right? So you say, well, great, Dr. Holman. So every time we see a circuit that looks like that, the transistor is saturated. Ha, ha, ha. Not so simple. And this is where people get into errors. Don't just look at a way something is drawn and say, oh, it must always be that way. No. I'm going to do exactly the same problem, but I'm going to change the value of that resistor. Now I'm going to set RD equal 10K, and I'm going to work the same problem. So once again, I'm going to assume saturation. It worked last time. Let's try it again. And if I plug in saturation, well, the numbers are all the same. VGS doesn't change. Nothing else changes for the ID equation. So ID is still equal to 400 microamps. Now what is VDS equal to? Now VDS is equal to 5 minus ID times 10,000, which is equal to 1 volt. So, is VDS greater than VGS minus VT? Is 1 volt greater than 3 minus 1, 2 volts? No. Obviously, I violated the boundary conditions. This cannot be insaturated. It cannot be in saturation. If it's not in cutoff and it's not saturated, what's the only thing that's left? It's got to be in triode. So I must be in triode operation. And therefore, ID must be equal to K prime N times W over L times VGS minus VT times VDS minus VDS squared over 2. Problem is I can't solve that equation by itself. I need to also add the VDS equation. So if I plug the numbers in for the top equation, what I'm going to get is this is equal to 200 times 10 to the minus 6 times 2 times VDS minus VDS squared over 2. And then I've got this equation, VDS is equal to 5 minus 10,000 times ID. So, 2 equations, 2 unknowns. What do I do at this point? Mathematica, absolutely. There's a problem here, guys. There's a square term in there. What kind of equation is this going to be with a square term? Quadratic. How many solutions am I going to get? 2 solutions, okay. Let us solve. If we solve, we'll get 2 answers. ID is equal to 138.2 microamps, or ID is equal to 361.8 microamps. So a quadratic equation gives me 2 solutions. Mathematica will give me 2 answers. And so what do we do now? Pick one? They're both right? What do I do? Check the boundary conditions. I've got 2 answers. Only one of those is going to meet the boundary conditions. Okay? So next time we'll come back to this. We'll check our boundary conditions, and we'll see which one of those answers made sense. Okay? This is what we're going to be doing, and we're going to work a few more of these problems next time.